All right, so we'll wait for a few minutes so that more of you can join actually in this class. So those who are attending this class, please respond in the chat box by saying anything, okay, so that I actually get to see your names. Once again, I'm repeating what I'm saying. Please write something in the chat box, okay? In the live stream, you see there is a chat box, okay? Please write something in the chat box so that I actually get to see your names, right? Right. Yeah. So that I can actually collect your attendance from there. All right. Thank you. Thank you for being here. So we're going to start the class shortly. So please tell me if the audio quality and the video quality are fine. If you cannot hear me properly, please let me know. Also, please confirm if you can hear me properly and see me properly. All right. So thank you very much. So we are actually changing the medium of instruction here. The operating procedure has been changed. So previously we were doing our classes using Google Meet. Just to repeat, we are going to actually once again have some certain doubt clearing classes through Google Meet. So there we can actually interact properly. But here, again, this YouTube live thing provides us with quite a few, what should I say, advantages here. All right. So let's get started here. Once again, whenever you have any difficulty understanding me, just raise a question in the chat box. I will definitely answer your query. Okay. Anytime you find something difficult to understand, or anytime you have any question, you can feel free to interrupt me and ask me a question. Okay. All right. So let me start by asking you a very simple question. Okay. So question is, who invented steam engine? Okay, that might be a very old question. I mean, you probably most of you have heard of steam engines, right? So question is, who invented steam engine? That's my question. So can anybody answer this question? Okay, those I see some of you actually attended the class in the previous year, and once again are here. Thank you for being here, but I would request you not to answer the questions. Okay. So those who are attending this class for the first time. Okay. So a very simple question I asked: who invented the steam engine? So can anybody answer? Okay, everybody is unanimously saying it's James Watt, right? Everybody is unanimously saying it's James Watt. All right. Anybody else has any answer? Anything else? Okay. Okay. Everybody is pretty much saying James Watt, James Watt, James Watt. Nice. Nice to see that you are on the same page. We all are on the same page. But let's see what Google says here. Okay. So Google is pretty much a know-it-all, and let's see what Google says. Okay. Just hold on. Yeah. Let's see what Google says. So if I search the inventor of steam engine on Google, this is what Google tells me. So as you can see, Google doesn't even mention James Watt. Okay, so if I do a Google search on inventor of steam engine, Google doesn't even mention James Watt. It gives me quite a few other names, right? So what exactly happened then? So who was James Watt? Right? We often associate the name of James Watt with the invention of steam engine, but pretty much all of you, okay, pretty much all of you mentioned James Watt as the inventor of the steam engine. But if I do a Google search and ask Google to tell me the name of the inventors of the steam engine, what we see is not the name of James Watt, but the names of other people. But my question to you is then, who was James Watt? What did James Watt do that so that his name is so closely associated with the steam engine that actually we often by mistake mention his name, the name of James Watt, in association with the invention of a steam engine? What did he create? Of course, he did create something, right? Even though, according to Google, and in fact, James Watt wasn't the inventor of the steam engine, but he did something, right? So that his name got associated with the invention of the steam engine. All right. So what is a steam engine? First of all, you essentially have some fuel, you burn it, okay, and by burning it, you generate heat, and with that heat, you boil up certain amount of water, okay, and when that water is boiled up, of course, it vaporizes, and you throw the vapor out of a nozzle, okay, on a certain mechanism, and that helps a wheel rotate, okay, that helps a certain thing rotate. So that's a steam engine, right? That's the basic principle of a steam engine. You burn up a fuel, and using that you heat up a liquid, okay, maybe water, okay, and you throw that water vapor through a jet, okay, on a wheel or a mechanism that makes a wheel rotate. Okay, that's the mechanism, okay, that's the steam engine, the fundamental idea behind a steam engine. But James Watt did not invent the steam engine, but what he did, he invented a mechanism of controlling the steam engine. So he invented a mechanism of controlling the steam engine. You have to understand the difference. He did not invent a steam engine, but he invented the mechanism for controlling the steam engine, okay? So what he developed is called a fly ball governor. So if I just look at the picture of a steam engine, you often see this picture, right? And in this picture, there is a mechanism standing right here. Okay, I'm not going to explain the mechanism right here. You can just search, do a Google search on fly ball governor. Okay, fly ball governor. And you would see that what James Watt did, he invented a mechanism of controlling the steam engine. What do I mean by controlling the steam engine? Essentially, again, a steam engine makes a wheel rotate. So you can actually put it on a vehicle, right? Put it on some sort of a vehicle. But unless you can control the speed of rotation, there is really no use of it, right? Unless you can control the speed of rotation, there is no use of it. Okay, so that's the difference. Similarly, it's very similar to the difference between a nuclear reactor and a nuclear bomb, right? A nuclear bomb does not have any control mechanism to control the reaction, okay, chain reaction, okay. But in a nuclear power plant, you have a mechanism in place that can control the chain reaction, okay. So everything is controlled. Just like that, if you have a steam engine which cannot be controlled, it's pretty much useless. It's just like a bomb, right? Okay. And similarly, this is exactly what happens. So all the vehicles nowadays are internal combustion engines, right? Use internal combustion engines. So essentially, combustion means burning something. So whenever you are driving a vehicle that runs on a fuel, okay, would actually combust a certain fuel inside its engine, right? All internal combustion engines. So literally, quite literally, explosions are happening inside the engine. And that energy that is derived from the explosions are converted into useful mechanical energy that can be used to drive a vehicle, right? So, but unless you can control the throttle, or unless you can control how much energy is derived out of that explosion, or how often or how powerful that explosion is, unless you can control that, you won't be able to control the speed of the vehicle. And if you cannot control the speed of the vehicle that you are driving, it's not a vehicle, it's a suicide machine, right? So it's literally of no use unless you can control the speed of the vehicle. So what James Watt did, he invented a mechanism. The mechanism is known as a fly ball governor. Okay, he invented a mechanism to control the speed that is derived out of a steam engine, and that's why his name is so closely associated with the invention of the steam engine. Even though he did not invent the steam engine, but he invented the mechanism to control the speed of the output speed, okay, out of the steam engine. So in other words, he made the steam engine useful. Okay, if he did not make the steam controller for the steam engine, essentially steam engine would not have been useful. Just like that. Okay, So in every so you can say that in general, unless you can control a certain mechanism, okay, unless you can invent or rather figure out a way of controlling a certain mechanism, okay, it's often quite obvious that under those scenarios, those mechanisms are pretty much useless for us. So you invented steam engine, it won't be useful unless you can control it. Okay, so control systems essentially boils down to inventing mechanism, understanding physical behaviors of systems and inventing mechanisms to control those physical behaviors of the systems. All right, so that's the fundamental motto behind the inventions, behind control systems, right? Don't think that control systems is a subject that is only related to electrical engineering. As a matter of fact, this is a multidisciplinary subject, and in fact, the book, the standard book, Modern Control Engineering by Katsuhiko Ogata, the standard book, the Katsuhiko Ogata, the writer of the book, is a mechanical engineer, in fact. Okay, so he's a professor at the University of Minnesota, and he is a professor of mechanical engineering. So again, in mechanical engineering, this subject is taught. In electronics engineering, this subject is taught. In electrical engineering, this subject is taught. And in many other branches of engineering, this subject is taught. And in fact, this subject is so vastly used in many different scenarios that this is considered a multidisciplinary subject. And this requires the knowledge of many different disciplines. Okay, and it is applicable to many different disciplines as well. So in that sense, it is not only a multidisciplinary subject, it is also an interdisciplinary subject, right? All right. So once again, just to repeat, James Watt is called the father of classical control. Okay. So he pretty much invented one of the very first modern control systems, if you want to say so. Okay. And pretty much you understand, you know that steam engine, the invention of steam engine led to industrial revolution, right? Led to the industrial revolution and led to the modernization that we are again reaping the fruit of even nowadays, right? So that led to the modernization of the world and the industrial revolution, as you say it. Okay, so essentially James Watt was the control systems engineer behind all that, all right? And that's why his name is so much associated with all this. So with all that aside, let's talk about what we talk about when we talk about control systems, all right? So again, I mentioned that in our course or in our subject, whenever we are discussing control systems, what we do, we try to figure out a way to understand the physical behavior of systems. All right. So we understand what systems are already. Right. We all know what systems are. Right. Systems are anything that has a boundary, maybe physical or logical, and that interacts with qualifying signals that approach it. Okay. And it generates signals as outputs. So those are systems, right? So understanding the physical behavior of a system is one primary goal, primary objective of a control system engineer. Okay. So if you are doing control system engineering, one of the primary objectives would be to actually physically model the behavior of a system, right? To be able to figure out how it behaves. So these are the things that as a control system engineer or in a control system course we actually encounter. Okay, so control system involves especially two things. Understanding, first of all, understanding the behavior of physical phenomena, mechanisms, different mechanisms, different structures, different objects, understanding the behavior. And how do we understand the behavior? By figuring out the physical laws behind all those and expressing them in terms of mathematics. So that idea is called mathematical modeling. So when we understand the physical laws behind a certain mechanism, okay, and certain structure, certain mechanism, certain phenomena, and when we understand the physical laws and express everything, that all the interactions and everything in terms of mathematical equations, we call it a mathematical model. So one objective of control system engineering is to develop the mathematical model of things. Okay, so that is one objective. Okay, and once we have the mathematical model of something, we would often try to control the mechanism. Okay, but before we can try to control the mechanism, we need to analyze the model, of course. So once we can analyze the model, so we need to analyze the model, and once we have done analyzing the model, we try to figure out a way of figuring out a way of controlling that mechanism. Okay, so controlling the mechanism or developing a controller. So these are the primary aspects of control system engineering. Okay, control system engineering involves mathematical modeling of any physical behavior. Okay, and then out of that mathematical model, we try to analyze the behavior in a more rigorous fashion. Okay, because whenever we describe something using mathematics, we can actually understand it more rigorously. Okay, the intricate details can be figured out, and then out of that we try to figure out a mechanism or a way of controlling that. Okay, so this control system is, of course, by means of all this, the idea of control system is one of the fundamental building blocks behind automation. So whenever we talk about automation, uh, we actually talk about the fundamental, one of the fundamental building blocks of automation, namely the control systems, right? So control systems essentially is that. So if anybody asks you what is control system, is control system is not a single thing. It's three things together, taken together. It's first looking at physical things, okay, looking at the behavior, natural phenomena, or any object, and figuring out its physical behavior by means of understanding the natural laws, okay, behind it, and expressing them in using mathematical equations. So that's mathematical modeling. And once we do the mathematical modeling, we try to analyze the mathematical model and then try to figure out a way of controlling that mechanism, way of developing something that automatically controls that mechanism. Okay, so this is, all these together is known as control systems. All right, so that's your subject, that's what you are going to study. Okay, but before I proceed further, so let's clear up what we have in the syllabus. We have quite a few mechanical systems to consider. We also have quite a few electrical systems to consider. So we are going to design certain electrical systems and certain mechanical systems, and we are also going to look at certain electromechanical systems. Okay, namely motors, okay, mostly, okay, that can be actually used to control mechanical systems using electrical signals essentially. Okay, so we can pass in electrical signals as inputs to the motor, and the motor can generate mechanical output to control certain mechanical mechanisms, right? So that's the understanding here. We're going to apply a certain, we are going to have certain electrical things, certain mechanical things, and being discussed in this course. Also, I mentioned in our last discussion that this subject, most of the theoretical aspects of this subject will be have come from like late 1940s or 1950s, early 1950s. And back in the day, people did not have computers or did not have calculators. So often the very complicated calculations involving complicated differential equations were actually solved in very, what should I say, very effective and very computationally effective ways. Okay, so people developed what they had to develop, right? Back in the day when people did not have computers, people invented the aeroplane, right? So that involved a lot of calculation, a lot of complicated differential equations, not only ordinary differential equations, but partial differential equations. So people invented ways to figure out how to tackle those problems without having a device that can compute all those things. Okay, so again, we are going to see that the major emphasis in the theoretical aspect of the subject will be behind developing techniques that can ease our calculation. Okay, so the least amount of calculation we can do, the less the amount of calculation we can do is the better. Okay, so it's often our goal in this subject to reduce the amount of calculation that might involve that might be involved otherwise. Okay, but nowadays we have computers, so we will of course make use of the computers. Of course, we are going to use the control system library in Python. Okay, so again, I mentioned that we are not using MATLAB, we are not using Scilab. In fact, we are using Python for doing all of our computation regarding this course. All right, so we are going to do Python programming throughout this course regarding whenever we need it. Okay, and that's one part of the course. Okay, just keep that in mind. All right, so with that aside, I would just wait for a minute and allow you to ask me questions in case anything crops up in your mind. Okay, you might want to ask anything. I just paste it in the just type it in the chat. All right, so just one more suggestion in case you don't have anything to ask, since we're already interacting through the chat. If you don't have anything to ask, just write all clear or something so that I can actually have certain feedback, and I will tell you why feedback is important in life. Okay, shortly. So in case you have nothing to ask, just write it's all clear or something so that I can actually see that you understood it, right? With that said, I can told you that these are the three aspects of the control system engineering in general, right? And our course is divided as such. We are going to actually involve, rather 30% of our course will involve developing mathematical models. Okay, not 30%, around 25% of our course will involve developing mathematical models of things. All right, and a better part of the half of the course, I mean at least half of the course will involve different analysis techniques. Okay, so 50% of the course is based on analysis techniques. Okay, different techniques for analyzing the mathematical model that we develop for systems, and the rest of the course will be developing controllers to control the mechanisms, the behavior of the systems. All right, so that's going to be the course structure. If you the course structure. Okay, here. Okay, we are going to put certain amount of time to develop the mathematical models, both for electrical and mechanical and electromechanical systems, and then we are going to develop certain techniques that can allow us to analyze those mathematical models easily and conveniently. Okay, certain convenient techniques with, again, the minimal amount of calculation required. Okay, and then we're going to use the mathematical models and the analysis that we did on them to design controllers for different systems. Okay, because that's the ultimate goal. The ultimate end goal is to design an automatic controller that automatically controls the thing without manual intervention or minimal amount of manual intervention. Okay, so that would be the objective in most cases. Okay, so but in order to design a controller, we need to go through the first two steps first. All right, with that being said, let's start our actual topic today, and that's going to be control system topology. Okay, so let's do one thing. Let's bring this section from here. Here. All right, so we're going to talk about control system topology. All right, so let's start the technical discussion here. All right, so again, since you already did signals and systems, you are familiar with how we describe systems. We describe systems often using a box. This box is often a black box, so we don't necessarily know what is there inside and how it is constructed from the inside. But we know how it behaves. Okay, we know how it behaves. So again, there are two types of modeling techniques. One is called the black box modeling techniques, and the other one is called the white box modeling techniques or glass box modeling technique. Okay, so in a black box modeling technique, just we're going to again describe this in our modeling classes. But in a black box modeling technique, what we know essentially, we know how it behaves or how it interacts with different inputs. So if I give the system certain inputs, how it interacts with the input and how it generates the corresponding output. So that is what we are aware of in case of a black box model. Okay, someone is asking me to actually speak a little slower. All right, so I will try. Okay, so in case of a black box model, what we do, we don't really know what is there inside the system. Okay, instead we know the input output behavior of the system. Okay, so if this is the input, what is the output, how it interacts with different inputs. All right, so that is what we know about the system. But on the other hand, there is another way of modeling systems, or another paradigm, I would say, another paradigm of modeling systems that we call a white box model or black box or a glass box model. Okay, I'm going to repeat, don't worry. Okay, so in a glass box modeling technique, instead of having the prior knowledge of how the system interacts with the inputs and outputs, instead we know what is there inside, what it is made of, and how everything interacts. Okay, so in a glass box model of a system, what we know, we know all the internal behavior of the system. We know how it is made, what it is made up of, how everything that is there inside it interacts with each other, all the physical equations, mathematical equations that involve the physical, that describe the physical interaction between all those objects that are inside the system. Okay, and out of that we ultimately figure out how it interacts with external inputs, okay, and how it generates output, okay, that can be passed on to certain other devices that are external to it. Okay, so that's called a glass box modeling. Once again, to repeat, in a glass box model or a white box model, often called, in a white box model, we know the constituent parts of the system, we know how everything that is there inside it works, okay, and how they interact with each other, and based on those equations we finally figure out how it interacts with external inputs and generates outputs. Okay, so that is something we understand. But for a black box model, we do not really know, or rather do not really bother to know, I would say, rather we do not really bother to know what is there inside for a black box model. Okay, we do not really bother to know what is there inside for a black box model. We instead just try to stay happy by knowing the behavior between the input and the output. So only the behavior of the input and the output, or the interaction, or rather the mathematical relationship between the input and the output, is known to us. Okay, if this is the input and this is the output, what is the mathematical relationship between the input and the output? That is only known to us. Okay, and nothing about what is there inside the system is known to us for a black box model. All right, so these are the two types of modeling paradigms. Okay, we can either describe something as something that interacts with external signals and generates these outputs, so inputs and outputs, without actually telling you what is there inside or how it actually internally works. That's called a black box model. And for a glass box model, we know about the input and output and their interaction, okay, the relationship between the input and output, but also we know how the system is constructed from inside. Okay, everything about it, right? Quite obviously, I believe you understand that glass box modeling is more difficult than doing a black box modeling. Okay, but we will see later on that when our modeling classes start, when we actually discuss the mathematical model of things, we would approach with a glass box paradigm. What we are going to do, we are going to actually look at different things from the inside, okay, how different things interact from the inside, okay, and then try to figure out how the whole thing would interact with external signals. Okay, for example, let's consider a motor, for example. Okay, say we have a motor, for example, maybe a DC motor, right? So in order to develop its mathematical model, okay, we would actually look into the system, okay, look into how it interacts, okay, how the armature magnetic field reacts with the field's magnetic field, and how it rotates, all the mechanisms that is actually happening inside the motor. And out of that, we are going to figure out if this is the voltage across the armature of the motor, for example, then what will be the output, what should I say, output frequency, rather output rotational frequency, okay, output speed, rotational speed, output position, for example, or amount of torque that is generated, etc., etc. All right, and out of that we are going to actually figure out how to control that mechanism. Okay, so the objective often is to start with a glass box model or glass box paradigm, and then to figure out from the glass box paradigm an interaction or a relationship between input and output. Right? You understand what I'm saying? We try to first of all look into the system and then figure out, okay, these are the interactions, and let's develop a mathematical model that gets rid of all the complexities and only keeps us, or rather gives us, a very simple equation as far as practicable, a simple equation that describes the relationship between the input and the output, disregarding everything that is there inside. So we first look inside, figure out how it interacts, okay, and then try to figure out a relationship between the input and the output, and then we get rid of all the complications. Okay, we only then are interested about the input and the output, okay, how they are related mathematically. So we start with a glass box model, we end up with a black box model. But why are we interested about black box models? Because whenever we are trying to go to the next steps, the second step where we analyze the system, we consider the systems to be black box modeled. Okay, so when we are doing a mathematical modeling, we consider the systems to be glass box modeled. Okay, so essentially we develop the model ourselves by knowing all the interactions, physical interactions behind the system. But when we are actually doing analysis, we would disregard what is happening inside the system for the most part, but we are only going to limit ourselves to the understanding of how the system interacts with input and the output. Yes, the term glass box and white box are the same term. Okay, some people call it a glass box model, some people call it a white box model. It's pretty much the same. Okay, the same thing. Okay, the same name. All right. So that's the control system topology. The paradigms, modeling paradigms. Okay. So this is still not control system topology. These are the modeling paradigms. Okay. These are the modeling paradigms. So these are the ways in which we actually develop the model. So just keep in mind that none of them is actually sufficient by their own. Okay, so you cannot have a black box model unless you have a glass box model. You cannot have either of that. So essentially both type of paradigms are needed all at the same time, right? But whenever we are analyzing something, we are using analysis techniques, we actually talk about the black box models only. And consequently, whenever we are designing the controller, we also look at the black box model only. Okay, so black box model, once again to repeat, black box model gives us the mathematical relationship between the input and the output, and it does not talk about what is there inside. Okay, and the glass box model or a white box model actually tells us everything that is there inside, and out of that, mathematically we are responsible for figuring out the relationship between the input and the output. So from a white box model, we actually end up with a black box model. We develop a black box model. Okay, to simplify our analysis techniques, because analysis techniques would require that we have a black box model. All right, so those are the design paradigm, or sorry, modeling paradigm, I would say. All right, and then let's talk about the control system topology. So here is the what should I say, the most important thing for today's class, right? All right, so up to this point, before we actually proceed to the next point, into control system topology, up to this point, if you have any query, just make sure to ask. Just make sure to ask. Okay, someone is asking me to repeat, so let me repeat the last part of what I said. Okay, so whenever we are doing the mathematical modeling of a physical system, because I told you that's the primary part of the first part of a control system, right? We do the mathematical modeling. We try to understand how the system behaves. Okay, we try to look at it using a glass box model. The idea is, consider an electrical circuit. Okay, we would try to figure out it as an electrical circuit. We would actually try to figure out the interaction between all the components inside that electrical circuit. Okay, and based on that, ultimately we are going to end up with result that tells me, okay, if you do this, then that happens. Okay, from an input output perspective. Okay, so whenever we are actually looking at the electrical circuit, bare electrical circuit inside that system, we call it a glass box model. Okay, glass box approach rather. Okay, and out of that glass box approach, then what we can do, we can figure out how it behaves with external inputs. Okay, and when external inputs are fed to it, what it generates. Okay, consider a mobile phone charger, for example. Okay, so there are so many complicated electronic components inside that mobile phone charger, right? So of course, if you want to figure out how it interacts, what it does really, you need to be able to figure out what the internal components do and how the internal components of that mobile charger interact with each other. Okay, and ultimately what you have is a box. Okay, and the ultimate result is that if you put that box or the mobile phone charger on a power outlet, okay, it will receive 240 volt AC or whatever, 110 volt AC. Okay, it will receive that much voltage AC, and it will generate, say, 5 volt DC. Okay, yes, so someone is asking, so can't a glass box system also work as a black box? Yeah, yes and no. The answer is yes and no, right? So the thing is, a glass box model, the black box model is a simplified version of a glass box model, okay, or a white box model. Okay, in a white box model, you pretty much depict the entirety of the internal behavior of the system. Okay, but for a black box model, you clobber up everything, only describe how the external input generates the output, how it interacts with external input and how it generates output, only the relationship between the input and the output. Okay, okay, someone is saying, why would I say 110 volt? Of course, if you are living in the US or the American states, for example, the voltage there is 110 volt. Okay, so as I was saying, consider a mobile phone charger. Okay, so the black box model would not talk about anything that is there inside. It will only tell you, black box model of a mobile phone charger would tell you, okay, if you put it on the mains, okay, if you put it on the power outlet, it will generate a 5 volt DC. Okay, if 240 volt AC or 110 volt AC goes into that, it will generate 5 volt AC or 9 volt AC or whatever. Okay, sorry, 9 volt DC or 5 volt DC. So that's the black box model. Okay, it only tells you what input will generate what output, or rather the relationship between the input and the output. It will only tell you that. Okay, but the glass box model will tell you how everything happens inside this. For considering 110 volt, I was just talking not about India. Okay, I was talking about other countries, other Western countries where you have 110 volt mains power supply. Just like in our mains, we receive 240 volt. In many Western countries, rather in America mostly, people people have 110 volt supplies. Okay, disregard the voltage. What I mean to say is that if you take a mobile phone charger and put it on the power outlet, the device, okay, that system, the box is receiving certain input and it is generating certain output. We know it is receiving 240 volt AC and is giving me 5 volt DC or something like that, maybe 9 volt DC, maybe 12 volt DC, something like that. So we know what input generates what output. Okay, so that interaction is the black box model. Okay, that knowledge is the black box model. And in a white box model, you depict everything that is there inside it. Okay, all the interactions between. Okay, so whenever that AC 240 volt goes into the mobile phone charger, first it goes into a rectification stage. Okay, it first goes into a rectification stage, so it becomes DC 240 volt. Okay, something like a DC 240 volt. Then out of that rectification stage, there is an inverter stage. Okay, that inverter inverts it back to AC. Okay, 240 volt AC, but now not at 50 hertz, but at some hundreds of kilohertz. Okay, and then that is again that inverted version, that rectifier inverted version is then passed through a transformer. Okay, so there is a relationship that tells you that if we have a transformer for higher frequency supplies, the size of the transformer shrinks essentially. So if you have a 500 volt ampere transformer that runs at 50 hertz, this will be this big. Okay, this big, for example, pretty heavy. But if you have a 500 volt ampere transformer that operates at, say, for example, 50 kilohertz, it will be this big. Okay, so the size of the transformer reduces if the frequency is higher. Obviously, there are other considerations. So that 240 volt is first rectified, okay, made into 240 volt DC, and then that is inverted, okay, using an inverter mechanism. Okay, and that inverter mechanism will actually invert it to an AC signal, but at something like 100 kilohertz. Okay, then that AC will be passed through a transformer, and that transformer will convert it to step it down and convert it to a lower voltage, for example. Okay, step it down and convert it to a lower voltage, maybe 12 volt AC, and that will once again be rectified to 12 volt DC. And then you have a DC to DC converter, like a chopper, okay, buck converter. Okay, and that will chop up the voltage, and through a filter mechanism, okay, it will generate the 5 volt DC or 12 volt DC or 9 volt DC. That is, all these things happen inside that small mobile phone charger of yours. Okay, so this is called an SMPS mechanism. Okay, switch mode power supply. But what I'm telling you is that all these internal behaviors, if you try to understand all the internal behavior, if you model all the internal behavior, what you develop is a black box model. So it's a glass box model or a white box model. Okay, but if you just say, okay, it receives 240 volts and by receiving 240 volt, it generates 5 volt out as output. That then you are talking about the black box model of the system. See that if I am making things clear here. Okay. For all our analysis techniques, we only talk about black box models. We only are interested about the interaction between the input and the output. All right. Just hold on for a second and ask in case you this is still not clear. All right. So again, if it is still not clear, try to ask once again. I would repeat. Okay. Okay, someone has a very interesting question and a very practical question. Can we produce a black box model directly? Yes. In fact, that's one, what should I say, one paradigm of this. Okay, we can sometimes produce a black box model without actually having a glass box model. Okay, we can actually produce a black box model without actually having a glass box model. That is quite doable. Okay, that is quite doable. And there are different techniques. Okay, different techniques that can be employed to actually develop a black box model. Okay, we can do that really. Okay, so let me just tell you the names of those techniques. These are mostly mostly fall under the category of system identification techniques. Okay, there are techniques called system identification techniques. You can just do a Google search, you will end up with quite a few mathematical complicated mathematical details. But there are techniques which fall under the umbrella of system identification techniques, which try to identify the black box model without figuring out the glass box model. Okay, so let me tell you that there are techniques which fall under the umbrella of system identification techniques, which allow us to figure out the black box model without actually knowing the internal glass box model, without actually knowing the internal behavior. So system identification is once again another subject. It is an advanced topic in signal processing mostly. Okay, but this is also a part of control system engineering. Okay, so we have a very small discussion on system identification later on in the course when we talk about frequency response. Okay, so when we talk about frequency response analysis, we can actually use the frequency response of a system to figure out the black box model of the system without actually knowing the glass box model. All right. All right, so we can actually use the frequency response technique. So that's one that is one system identification technique. Okay, so that so once again we have a question which says, can we design a black box, say a charger that takes different input but certain output only? Okay, so the moment you are using the word design, we are not designing anything. The thing is already there. Okay, the thing is already there. We are trying to figure out its behavior, either internally or externally. Okay, we're just trying to figure out its behavior. But whenever we are actually developing something, whenever you're actually creating something, you of course need to know how things interact internally, right? Right? But whenever we're talking about modeling, we are already understanding that it is there for us. We are just trying to understand the behavior. Okay. Got it? All right. So once again, I'm just giving you time so that you can actually ask me questions. You can keep on asking me questions until your doubts are cleared here. All right, so I think we can actually move on to discussing control system topology here. All right, so we can actually move on to discussing control system topology. So I'm constantly looking at the chat box here so that everything is fine. Just all right. So as we were talking about steam engines from the very beginning, we would actually talk about a vehicle or a locomotive. Okay, a vehicle that moves. All right. Again, one second question. How can we make a black box without knowing the internal behavior? Okay, someone is saying, how can we make a black box model without knowing the internal behavior? As I told you, there are techniques, okay, which fall under the umbrella of system identification techniques, which can actually identify a system, or rather identify the black box model of a system, okay, without knowing what is there inside. Frequency response analysis is one of those techniques, okay. So using frequency response of a system for linear time invariant system, for LTI systems, if you know the frequency response of a system, you can actually develop the black box model without knowing the internal glass box model. Okay. Oh yeah. To answer your question, you need to have that system physically present with you. Okay. So in order to develop using a system identification technique to work, you need to have that physical system with you. Okay. So you can actually generate the frequency response of the system, and out of that you can actually figure out what's the model of the system, what is the black box model of the system. Okay. So frequency response can be used as a system identification technique for LTI systems only, for linear time invariant systems only. If it is not linear or not time invariant, then of course we have other techniques, other more complicated techniques that can actually tell you that. But yes, to actually have a black box model without knowing the glass box model, you need the system. Okay. All right. And the moment I say you need the system, if I am talking about the linear time invariant systems, then you don't even need the system. You just need the impulse response. Right? So having the impulse response for linear time invariant systems is the same as having the system itself. I explained this quite vigorously in the last class, last subject, I guess. Okay, so you know that, right? So if we are talking about linear time invariant systems, then having the impulse response is just like having the system. And by having the impulse response, we can actually figure out the model of the system, the black box model of the system, quite easily, in fact. Okay. So that's, again, one of the analysis techniques we are actually diving into. All right. So let's talk about control system topology. Now, what is the meaning of the term topology? Okay. What is the meaning of the term topology? Okay. So again, it's a concatenation of two Greek words, is topos and logos. Okay, topos stands for structure. Okay, and logos is the knowledge of something, knowledge of structures. Okay, so it is the knowledge of the structure of control system. Okay, that's control system topology. How, or rather, so I would rather call it control system terminology. So we're going to talk about topology and terminology. Okay, how what different things have different names. So different things have different names and they interact with different things in different fashion. So that terminology is we are going to discuss next. And topology essentially gives you the structure of everything, tells you the structure of everything and how it interacts, behaves. Well, fundamentally, what we have a system that we are trying to control. Okay, so that's again the fundamental objective of any study involving control systems. Okay, and again, just to tell you, today's class will not involve any mathematics whatsoever. But later on, from the next class onwards, we are going to have quite a few involved mathematical details, right? And of course, I'm going to teach you the mathematics alongside the course. Don't worry. So this is the fundamental part of any control system. That is the system that I want to control. So the system that I want to control is called the controlled system. So system that I want to control, okay, is called a controlled system. Okay, is there any confusion? So that's again the, what should I say, the fundamental piece of the puzzle. Okay, so there is a system that I want to control. For example, just case, it's okay. Well, there's another question. The internal behavior of the boxes can be same. Okay, I am not clear about the question really, what you are saying. Can you just repeat the question? I mean, elaborate the question. Okay, just hold on. All right, so this is again the fundamental cornerstone behind any control system. So that's a controlled system. For example, we were talking about the steam engine, right? And there the steam engine itself was the controlled system. Okay, controlled system, right? So let's talk about a vehicle or a locomotive, for example. Okay, so how many of you drive cars? Okay, cars or motorbikes or anything, motorcycles, or just hold on. Okay, sorry for the interruption. All right, as I was saying, control system is the cornerstone of behind any system, right? And say many of you actually drive some sort of vehicle. At least you know how to drive some sort of a vehicle, right? Maybe a bike or maybe a four-wheeler or whatever, right? So you know how to that how to drive a vehicle, right? So of course there are many complicated parts, okay, inside the vehicle. But let's say this is our vehicle. The control system itself is a vehicle. Okay, just try to understand, because this will actually give you a better understanding of what we are saying here. Okay, let's say the control system itself is the vehicle. So not a bad assumption, I guess. Okay, of course there are so many internal things and they interact with each other. Again, we are trying to look at this as a black box, with a black box approach. Okay, we are trying to look at this with a black box approach. We are not trying to what should I say, look at the internal behavior. All right, so if you have a if you drive a car or drive a bike, you know, if you roll the accelerator, okay, if you roll the accelerator, it will what should I say, accelerate, it will move faster. And if you release the accelerator and hit the brakes, it will actually slow down. Same for a car. Okay, if you hit on the accelerator pedal, so essentially the car will move faster, and if you release the accelerator pedal and hit the brakes, it will become slower, right? That's obvious. So you, as the driver, you can assume yourself to be controlling the car, right? So the car itself or the vehicle itself is a controlled system, and you as the driver is the controller of the car, right? You can assume it yourself to be controller, because you are sending signals to the vehicle, and the vehicle responds accordingly by either accelerating, either moving faster, or slowing down, right? It responds like that, right? So you can consider yourself to be a part of that system which interacts, so not part of the system, but something that sends certain signals to the control system so that it behaves intentionally, right? It behaves intentionally. So it behaves whatever your intention is. Okay, so that's a controller. Okay, the controller. Okay, the controller part could be you as a driver. Okay, so you are supposed to be sending certain signals to it such that it actually either accelerates or decelerates, right? Understandable. All right, but for the moment, this is the interaction. Say you are driving on a road, okay, and currently you are on a highway and you want to travel at 80 km per hour. So that's the desired speed you want. So essentially the input to the controller, or rather in your head, you know that you want your bike or your car to go with a speed of 80 km per hour. Okay, imagine a perfect road, no issues. All right, so now what are you going to do? What are you going to do? Let me ask you a simple question. So you want to travel at 80 km per hour. What are you going to do? Are you going to accelerate, or are you going to hit the brakes? Are you going to accelerate, or are you going to hit the brakes? What do you say? I want your answers. Okay, I'll be back just in a moment. But let me ask you the simple question. You want to travel at 80 km per hour. Are you going to accelerate, or are you going to hit the brakes? Okay. So we got quite a few different answers. Okay. Okay, just to go back, one of you had a question that the internal behavior is. The idea is that if have, say for example, we have two systems that have the same black box model, okay, but they can have different glass box models, okay, different internal behaviors, okay. Things can be constructed differently from the inside, but they might still behave the same way from the outside, okay. So a same system, having the same black box model does not ensure having the same glass box model, okay. I think that's understandable, right? Okay, so many of you are saying accelerating, we are going to accelerate. Yeah, I remember. Yeah, and some of you are saying it depends on the speed, and that's exactly the answer I expected. Okay, so I told you that you are driving a vehicle, you currently want to run at 80 kilometer per hour. What are you going to do? Are you going to accelerate or are you going to decelerate? Hit the brakes, right? It depends. It depends. You might be currently just traveling at 40 kilometer per hour, so you want to accelerate. Yeah, but maybe you are currently running at 100 kilometer per hour. So in that case, you are going to decelerate or hit the brakes, right? So that's the understanding here. You need to know what your current situation is in order to figure out what input you are going to provide to the control system. Again, once again, try to understand that the control system is the vehicle that you are driving. That's the control system. It does whatever you want it to do, whatever you tell it to do. And who is going to tell it? The controller. You are the controller here, right? But in order to travel at 80 kilometer per hour, what you are going to tell the control system is entirely dependent upon what the current situation of the system is, right? If the car is currently running at 100 kilometer per hour, you don't want to accelerate anymore. You want to slow down. But if the car is running at, say for example, 40 kilometer per hour or 60 kilometer per hour, you want to accelerate now. So whether or not you want to hit the brakes or accelerate depends on the current output. Hold on. Right, let's hold on. All right. So that's the so in order to know how fast you are traveling, so you need to know how fast you are traveling currently, right? So maybe currently you are running at, say for example, 40 kilometer per hour. So that's your current speed. Okay. Now you need to know what your current speed is, and based on that you would take a decision on whether you want to accelerate or decelerate, right? So you want to know this, you need to be able to know this, and you need to be able to compare this with this. You need to be able to compare this with this. So now imagine you are riding the vehicle without looking at the speed, with your eyes closed. Will you be able to have an idea of how fast you are traveling? Maybe you will, but maybe not, right? You probably not have any idea of how fast you are currently traveling, right? So if you are traveling blindly with your eyes closed, right, you need to look at your speedometer. Okay, so you need to look at your speedometer or something. You need to have some physical understanding of how fast you are traveling. Okay, so you need to sense how fast you are traveling, right? In other words, you need to be able to sense how fast you are traveling, either by looking at the speedometer or looking at the surroundings, looking at the road or whatever. Okay, some people who drive regularly have a sense of the speed automatically. Okay, some people who drive, most of us who drive regularly on a regular basis, we don't need to even look at the speedometer to change the gears and all, right? So we automatically figure out the speed at which we are traveling by just having a feeling, but that sense needs to be there. Okay, so in order to compare these two speeds, we need to be able to measure this speed in a technical sense, right? We need to be able to measure this speed. So what we say, we need to measure this speed using some sort of sensing mechanism. That sensing mechanism could be inside our head. Okay, it would involve our eyes, of course. Okay, but we need to have certain sensing mechanism. Okay, certain sensing mechanism, and that sensing mechanism would help us understand what speed we are currently running at. Okay, so we're just going to call this a sensing mechanism, or rather a sensors. Okay, it would involve our eyes also, right? So just it's a very overall idea here. Okay, you got this, right? So that will be the sensors, right? So, and then out of that, so this is your desired input or the desired output here, right? So you wanted to travel at 80 km/h. So that's the desired output. That's the desired speed of the vehicle. So this is the output, right? This is the output. But this is whatever is the input to the actual system is the desired output. So you want this output to match up with whatever you desire, right? That's the idea here. So what you are going to do, you are going to take a decision by comparing these two. And how do you compare this? Using a comparison mechanism. Now, of course, in the control system topology, the comparison mechanism is expressed using a circle. Okay, using a circle and with an X symbol there. Okay, and this is kind of the block diagram we draw. Okay, I think you can see this, and there is a minus sign here, there will be a minus sign here, and there will be a plus sign here, which tells you. So again, just to zoom it in, this is the symbol we had drawn. Okay, so here is a plus, here is a minus. So whatever, so if say for example the signal here, if I call this R, and the signal here if I call this B, okay, and whatever is coming out of that comparison, okay, if I call this E, then E is just going to be R minus B. Okay, so that's just a comparison operation. Okay, that is just a comparison operation. Okay, so you're going to actually compare whatever is the current output with what you want. Okay, so this is the desired output. So inputs are always desired outputs. Okay, so you want the output to be 80. So this is your desired output, right? Also often known as reference signal. So reference is essentially what you want in the output. Okay, so you want to compare them, and accordingly the controller, I mean you, are going to take a decision on whether to accelerate the vehicle or decelerate the vehicle. So accordingly, you are either going to accelerate or decelerate. Either you are going to hit the brake pedals or you're going to hit the accelerator pedal, right? So that way, whatever signal goes into the this signal that is going out of you into the car, okay, would differ. Okay, maybe you are very close to 80, right? You are not going to hit the accelerator quickly, right? You are going to slowly hit the accelerator in that case. Okay, right? So that's understandable, reasonably, I guess. So this is the signal that is responsible. So here, this is the signal which is going out of the controller into the control system, is responsible for making the controlled system respond, right? Right. So these are the signals that are involved here. Okay. So let's now call them by their proper names here. Let's now call them by their proper names here. Let's get rid of this so that I can actually draw it in a better way. Just hold on. All right, so this signal is often called R, often represented with a R here. But again, these are the standard topologies here. All right, this is often called R. We often express this as R. Okay. This signal that is the output of the system, we often call that. So let's just use a different color. We express that with a C. Okay, and this signal that is actually fed back by the sensors and compared here is called, often represented as B. The signal that is out of the comparator, goes out of the comparator, is called E, and the signal that goes out of the controller into the control system is called M. Okay. So now let's talk about the names of these different signals here. Okay. So R, of course, stands for reference. So R is the reference signal. So reference is again referring to the fact that this is the output you desire. Okay. And C is the controlled variable. Okay. So C is the output, but namely its actual proper name is controlled variable. Okay. Oh, someone is saying the symbol which is used for comparison. Okay. The symbol that is used for comparison is this symbol, this circle symbol. Okay, with an X, like the X-Men logo. Okay, circle with an X, for example. And here we have plus symbols and minus symbols. So essentially, this is a comparison operation. And in this comparison operation, whatever has a plus sign gets a plus sign, whatever has a minus sign gets a minus sign. So whatever is the output out of the comparator, okay, is an algebraic sum of that. So essentially, R minus B is the output here. Okay, output of the comparison. Similarly here, just in this figure here. Okay, so reference, okay, is compared with the present output. So for example, just as the previous example, if the vehicle is currently traveling at 80 km per hour, sorry, the desired output is 80 km per hour, but the vehicle is currently traveling at 60 km per hour, then E would be something like 20. Okay, something like 20. Okay, so it is going to tell the controller that you need to move faster. Okay, so the controller would actually hit the accelerator pedal. All right. So, but now, if for example, if the controlled output, which is referring to the present output of the system, just hold on. Right. So, for example, if you are currently traveling at 100 km per hour, what you are going to do? We are going to again compare them, and when you do R minus B under this scenario, it will be something like it would be something like minus 20. I'm just saying something like, because it will later on be slightly different. Yeah, if B is someone is saying if B is tells about the current situation, then how can it represent the output? Yeah, so someone is asking if C tells about the current situation, then how it represents output. Yes, the current situation is being considered to be the output. Okay, so here output is what the speed of the vehicle is currently, what speed the vehicle is currently running at. So that is something we call the output. Okay, that is something we call the output. So the output is the control variable which tells you about the current situation of the vehicle, essentially what the speed of the vehicle is, right? So many of you are saying when B is something like 120, for example. Currently I'm saying that the sensor is, a strict pass through, essentially. The C is passed through the sensor, essentially. Okay, ignore the sensor for the moment. Okay, assume that B is equal to C. Okay, let's assume B is equal to C, which often is not, just assume. So under that scenario, if this is 120, then E would be something like minus 40. That would tell the controller, okay, I have 40 km per hour in excess to what I want. This is what I want, and this is what I currently have. I have excess, so the controller will act accordingly and hit the brake pedals. Okay, will decelerate. So I think this is understandable, right? So this is just a comparison operation. Okay, that's a comparator operation. Yeah, I'm going to just talk about all these, the names or names of everything. So R is called the reference and C is called the output of the controlled variable. Okay, that is the variable that is being controlled. Okay, B is called the feedback signal, obviously. Okay, B is called the feedback signal. So just I told you in the very beginning of the class, even if you don't really have anything to say, still say something so that I know that you are there in the class. Okay, so B is known as the feedback. So B is the feedback signal. So you need to have a feedback in order to actually travel properly. In order to actually, what should I say, have a, in order to have a proper controlling mechanism. Okay, the controller needs a feedback. Okay. C, someone saying, so C is the output after processing. It is often not. It is essentially the raw output of the system. So the raw speed of the vehicle in this case. Okay, raw speed of the vehicle. Just by looking at the road or whatever, you don't really know exactly the speed. You need certain sensors, right? So the car will have certain sensors, and what you are seeing exactly what speed will be actually through the sensors, right? So B is exactly depicting the speed. Okay, C is the raw output, essentially the raw speed of the vehicle. Okay, C, can you distinguish this, right? So this is what you are actually measuring. Okay, so C is really the current situation of the vehicle, and B is what you have measured, the measured output really. The feedback is essentially the measured output. Okay, so what you have measured through sensors. Okay, so if you look at the speedometer in your vehicle, what you are seeing at, looking at, you are looking at B. And yes, R is the desired output. And yes, this is, for example, an example of controllers for any vehicle, right? So in that case, whenever you're talking about cruise control or whatever, the controller is often not a human. Okay, the controller is often, what should I say, a mechanism itself. Okay, it does not have to be a human. I'm just giving you an example so that you can relate. Okay, properly. So B is a feedback signal. Okay, all right. B is the feedback signal. So this is what you measure essentially. What you measure, things that you can measure are actually feedback. So this is the feedback signal, measurable things. Okay, but this is the raw output, the controlled variable. Okay, so the reference is called the desired output. Reference is also known as the desired output. So if your reference is 80 km per hour, what does that mean? It means that you want your vehicle to run at 80 km per hour. So the reference itself is the desired output. Okay. So I specified. So that again, someone is saying to specify B. I mentioned that specify. So B is essentially the feedback. Okay. B is feedback. I just did not have space to write it here. Okay. B is feedback. Okay, B is called the feedback signal. So whatever you measure out of the vehicle or whatever, okay, whatever is measured is the feedback signal. Okay. Okay. So feedback signal is essentially what you compare your reference signal with. Okay. Reference signal is essentially what you desire, and this feedback tells you what you have. Yes, I'm going to explain all the names. Don't worry. I'm going to explain all the names. Just you don't worry. Okay. So reference is the desired desired output, and B tells you what you have. So essentially R refers to what you want and B refers to what you have. Okay, so what you want is 80, what you have is 40. Okay, what do you need? You need more. Okay, you need more. But for example, if the reference is 80, so that means what you want is 80, but you have 120. Okay, so that difference will tell you, by comparing these two, it will tell you that, okay, you want less than what you have. Okay, so B is essentially what you have and R is essentially what you want. And the difference between what you have and what you want is called the error signal. Okay, this E stands for the error signal. The very actual proper name of this is actuating error signals. So this E is called actuating error. Actuating error signal. Actuating error. Oh, of course, everything is signal, right? So actuating error. The name of this is actuating error. Okay. So not exactly an error signal, but it's an actuating error signal. So that actually tells you the difference between the reference and the feedback signal. Okay, it's called an actuating error signal. All right. So that actuating error signal is going into the controller. Here the controller is the driver. Okay, the driver sees that, okay, I want to run at 80 km per hour, but my vehicle is currently running at 40 km per hour. So that is the error signal that went into the head of the driver, right? So you know, okay, I still have to speed up. I have to speed up and I have to make my vehicle go 40 kilometers per hour more than what it is currently running at, right? So that difference, that actuating error signal is now working in your mind. So this comparator is also inside your mind, okay? Try to understand, okay? So now the controller, how will you respond? Since you see that your vehicle is running slower than it should, you are going to hit the accelerator. You're going to hit the accelerator, and that hitting the accelerator is what the system responds with, right? So this M is what you are sending to the system itself. M is what you are sending to the system itself, the control system itself. So you are either hitting the accelerator or you are hitting the brakes, okay, releasing the accelerator, right? In a car, of course, if you want to hit the brake, you have to release your right foot from the accelerator, right? So essentially the same thing, right? So if you want to hit the brake, you have to release the accelerator. So yeah, how fast you are going to hit the brakes, or how fast you are going to accelerate, or how slow you're going to do that. So that will be your input, the input of the controller into the control system. So this is what the controller generates. So this M is the signal that the controller generates, okay? And this signal that is generated by the controller is fed into the control system. This M is thus known as the manipulated variable. The formal name of M is the manipulated variable. Okay, so this is the signal that is actually going from the controller into the control system. Okay, that's called the manipulated variable. All right, so that's a very basic control system topology. Okay, so if you have any question regarding the names and the nomenclature here. Instead of calling it topology, let me call it nomenclature. So we just talked about the names. Nomenclature means, again, the naming conventions here. All right. Which one? So someone is saying what is it called? Which one is called what? What are you asking about? Please ask clearly so that I can actually have an understanding of what you are asking actually. Okay, it's called control system topology. As I said, it's called control system topology. Okay, the standard control system topology. Okay, the nomenclature, the particular names of different things, names of different signals. So this whole thing is control system topology. Okay. Often, since it's a feedback control system, you can see there is a mechanism for feedback. It is often called the feedback control system topology. So let me just mention that with that particular name. It is feedback control system topology. So in this figure, you see what you see is feedback control system topology. Okay. All right. So this is the feedback control system topology. But there are two more things that I actually need to mention right here. Okay. There are two more things that I need to mention right here. So you have heard of two words, namely disturbance and noise. Okay, you have heard two words, disturbance and noise. Okay, disturbance and noise. Now do tell me, Are they different or are they the same thing? Disturbance and noise. Are they the same or are they different? Do you think are the same or are they different? You have heard about noise and you have heard about disturbance. So are they the same thing or are they different? So can anybody tell me what is disturbance? Okay, someone is saying they are different. Yeah, indeed they are different. Quite different in fact. Okay, quite different in fact. Let me just explain what disturbance is, and I shall then explain what noise is. Right. So disturbance. Okay. So you are running the vehicle. Those of you who run the vehicle, drive a vehicle, you pretty much have faces, right? The road is never perfect, right? In a perfect world, everything will run perfectly. But nothing is perfect, right? The road is not perfect, the weather is not perfect, the traffic around you are not perfect. Nothing is perfect, right? Nothing is really ever perfect, right? So you always need to actively control the control system. Okay, you always need to actively control the control system. I remember I was riding my bike one day, and all of a sudden a crow dumped on me. Okay, a crow dumped on me. I just wanted to look above my shoulder. I just tried to look above my shoulder. Then what happened? I just wanted to see the situation. And that very moment, there was an auto rickshaw right in front of me, which hit the brakes. So I immediately hit that auto rickshaw. Okay, that is something that happened. So for a moment, I did not control my vehicle. I did not. What should I say? For a moment, I did not take the inputs from the sensors. Okay, I did not look at the road right ahead of me. For a moment, just for a moment, for a fraction of the second, right? And things changed right in front of me. The auto rickshaw was moving fast, but then it hit brake. I was also supposed to hit the brakes. Okay, I was also supposed to hit the brakes, but I did not. So nothing in the world is perfect, right? So you always need to keep on controlling the vehicle. Always need to keep on controlling the vehicles in order to keep the desired output at keep the control variable at the desired value. So if you want to run the vehicle exactly at 80 km per hour, okay, exactly at 80 km per hour. Okay, someone of you are actually giving me the correct answers, but let me explain it anyway. Okay, so you always need to what should I say? Always need to control, keep on controlling. Just to give you an example. So for example, currently you are running at 80 km per hour. Sorry, you want to run at 80 km per hour. Currently, you are also running at 80 km per hour. Okay, so the error signal is 0. Essentially, the error signal is 0. Okay, very nice. But question is, does the controller still have to do anything? Does the controller still have to do anything if the desired output is the same as the present output? What I want is exactly what I have. But my question is now, does the controller have to do anything? Does the controller have to do anything? In a perfect world, yes, the controller does not have to do anything. In a perfect world, in this scenario, when you achieve this tranquility, achieve the situation where the output is exactly the same as the input, so what you want is exactly the same as what you have. Okay, you don't really need to do anything. Okay, don't really need to do anything in a perfect world, but nothing is perfect. Okay, there might just be a pothole right in front of you. Okay, and that would deviate your speed, right? Someone might be braking in front of you. You won't have any other option but just to brake. Okay, you see, that's the problem here. Even though you have currently achieved what you wanted to achieve, but in order to keep that achievement, you still have to keep working. You have to still keep a close eye on everything, right? And that's true for our lives as well. Okay, just because you have achieved your goals does not mean you have to stop right there, because if you stop, your goals will automatically fade away from you. Okay, that does happen. So don't ever be content with your life. Okay, don't ever be happy with also I have achieved my goal, that's the end. No, that's not the end. If you think like that, if you think that okay, I have achieved the goal, that's the end, it's not going to end well for you. Okay, and so does happen for the system, because nothing is perfect and the world is not perfect. Okay, we always have disturbances affecting the controlled system. So we always have disturbances affecting, and we have disturbances happening on the laptop screen. Okay, anyway, so we have disturbances that are affecting the control system. Okay, so disturbances are affecting the control system. So let's just write this as, so this dog is shouting, dog is barking, people are shouting. See, just hold on. Okay, so disturbance is an external signal. Okay, just hold on for a second. Just hold on for a second. Okay, so here, once again, look at this. So disturbance is an external signal that affects the behavior of the control system. Okay, so D stands for disturbance. Okay, disturbance. Now let me ask you one simple question once again. Is disturbance undesired? I explained that since you have disturbance, you need to always, the controller needs to always keep on acting to make sure that the output is, that what output you have achieved is maintained. Okay, to maintain the output, the controller needs to always keep on acting, even though you have achieved zero error situation. Okay. Question is, okay, dogs are barking. Just one. Okay, so many of you are agreeing. I think you would unanimously agree that disturbance is undesired, right? Okay, unanimously agreeing that disturbance is undesired. In a sense, yes, disturbance is undesired, but in a sense, no. Let me tell you, imagine a perfect world, there is no disturbance whatsoever. You want no disturbance. Okay, I mean, no one is going to stop right in front of you. Okay, there are no potholes on the road. There are nothing. There are no disturbances. So you want to run your vehicle exactly at 80 km per hour. You have achieved that speed. Okay. So you, as a driver, don't need to do anything. You don't need to do anything. Then my question is, what is your utility? Okay. What is the job of the controller if there is no disturbance? Once the desired output is achieved, if there are no disturbances, then there is no job for the controller left. The controller becomes useless once the desired output is achieved. When the desired output is achieved, the controller pretty much becomes useless, right? Try to understand. Once the desired output is achieved, the controller pretty much becomes useless in a perfect world where there are no disturbances, right? But the controller does exist. Controller is useful because disturbance is there. Okay. So in French, there is the term called raison d'être, stands for reason for existence. The controller exists because disturbances exist. Okay. So disturbance is the reason for the existence of the controllers. The controllers do exist because the disturbance exists. Otherwise, by reaching the desired output once, we would have been there for the desired output forever, right? Yeah, nothing would have been needed. Nothing would have been needed. Once we would have actually reached the desired output, neither the sensors nor the controller, nothing would have been needed, really. Okay. Right? None of these would have been needed. Okay. We have achieved nirvana. Everything is fine. Nothing is needed anymore. Okay. So, but that's not the case. Disturbance is there, and since disturbance is there, we have to have a controller. So disturbances are the raison d'etre for the controllers, reason for existence of the controller. Okay, so disturbances are there. You cannot say disturbances are undesired. Okay, disturbances will be there, and that's why we design controllers. We design controllers to tackle those disturbances. Okay, got it? Okay. Yes. So the controller needs to be there because disturbances are there. So in a perfect world where there are no disturbances, the controller should be there, but up until the desired output is reached. Once the desired output is reached, there is no need for the controller and anything associated with it, like the sensors and etc. Nothing is needed. You have reached the final output. Done. Story is over. Right? That's not the case. All right. So disturbances are not really undesired. Really, they are already there. You cannot really do anything about it. The disturbances are catered by the controller. So controller is responsible for catering towards the disturbances. Okay, got it? Then there comes noise. What is noise? Let me just tell you before I even talk about noise. Noise is pretty much undesired. Okay, noise is what tells you that. So for example, I have this thing, and noise would tell me, okay, no, you don't have this thing, you have something else. Okay, someone is asking a very interesting question. What if the desired output is changed? What if the reference output, what if R is changed? Yes. If R is changed, then once again the controller needs to be engaged until the desired output is reached. Then again, there is no job for the controller. But then again, there is no job for the controller. Right? Stupid dog is keeping on barking. Alright, so as I said, sorry, I forgot to. Yeah. So I was saying that if the reference changes, then yes, the controller would be momentarily engaged. So the controller will be momentarily engaged, and the new reference value or the new desired output value will be reached. Okay, but once the desired output value is reached, then once again the controller will stop working. The controller will become once again useless. Okay, so reference value changed, the controller got engaged once again, and it hopefully made the control system reach or achieve the desired output, and then the controller is no longer needed, right? But the controller is actually needed all the time. Why? Because of disturbance. Since disturbance is there to maintain the control variable, the controller is needed all the time. The controller is required all the time. Okay, just because disturbance is there, there will be certain unknown behaviors happening, and the controller will need to cope up with that. Okay, make sure that the control system will cope up with that. So disturbances are there, and that's why controllers are there. Okay, the controller's sole objective under this scenario. Okay, if it is not just reaching the output, once it reaches the output, the controller's sole objective is disturbance rejection, trying to get rid of the disturbance by catering to it. Okay, so disturbance is like something that you cannot get rid of, you can only cater to it. Okay, you can only try to keep it happy. Whatever changes it wants you to make, you can just try to revert those changes, right? So that's the idea here. Yeah, but someone is saying you're putting a fantastic what should I say, philosophical point. You cannot say disturbance is desirable because we want to have a controller. Yeah, no, I never mentioned disturbance is desirable. I only said that disturbance, we cannot get rid of disturbances. Okay, disturbances will be there. Okay, disturbances will be there, and you see, nothing would really have existed unless there were disturbances. So I can give you a very big philosophy lecture here, but nothing would really exist ever unless there were disturbances, unless there were unforeseen changes. Okay, unless there were that, there were those, nothing would really have existed ever. Okay, so if everything worked perfectly, exactly, okay, nothing would really have existed. Nothing really would have worked ever. Okay. So very basic physical interaction like friction. Friction is again one electromagnetic interaction. That very basic force of nature, friction, is one sort of disturbance, right? Right? If you are running on a very smooth road or whatever, thing will come to a stop at a certain point of time because of friction. Okay, that's a disturbance. So there is really nothing we can do about it. So yes, disturbances are not desirable in a sense, but there is nothing we can do about it. Okay. Of course, if the disturbances are unlimited, then yeah, there is of course a capability limit of everything. The control system and the controller, both of them have their limits of capability, right? So if the disturbance exceeds that, then there is nothing you can do about it. Let's go to the next point, noise, right? So right off the bat, let me say noise is undesirable. So noise is again represented with N here, but noise does not affect the control system. Noise only affects how we perceive about the control system. Okay. So just to give you a real physical idea about this, what is noise? For example, in our life, personal life, practical life, so sometimes we think very highly of ourselves. Okay, that might be noise in our life. Okay, so through these sensors, what we see, okay, can be affected through noise. So what we see through the sensors can be affected through noise, and this is completely undesirable. In a world where noise is not there, would be a very nice world. The controller would still be needed, everything is still fine, but it will be a very nice world. See, what a noise can do. For example, the vehicle is currently running at, say for example, 40 km/h. Okay, but noise can come in the way of the sensors and give you a wrong measurement. It could tell you that okay, you are not running at 40 km/h, but instead you are running at 60 km/h. That is giving you a wrong information. So noise can actually adulterate or modify unintentional modification into your measurements, right? So noise affects measurements. Noise does not affect the control system. So this is the topological difference. Okay, noise does not affect. So disturbance affects the control system, but noise affects the measurement. Sensors are used for measurement, so noise affects the measurement. Okay, noise is highly undesirable. You don't want noise because noise will affect the measurement, but the measurement should be perfect, because based on the measurement you are going to take the decision, right? Based on what you are measuring, you are going to compare that with the reference, and you are going to generate that error signal, and based on that error signal you are going to take the decision. The manipulated variable is essentially the decision that the controller takes. But if your measurement is wrong, then the error signal is also going to be wrong, and your decision is also going to be wrong. So noise directly affects your decision making behavior, what decision you want to make, and that is also true in our human lives as well. Okay, so whatever noises, whatever wrong perceptions we have in our lives would often result into wrong decisions being taken by us. Okay, whatever wrong perceptions we have about ourselves, okay, is like a noise that will give us wrong measurements. Okay, and that will actually help us taking wrong decisions in our life. Okay, that's a bad thing really. We don't need noise. Okay, we want to cater to all the disturbances in our life, all the obstacles in our life. Okay, those will be there. We need to overcome. So the control system will need to overcome all the obstacles, all the disturbances. But noise is undesirable. Noise might make you fail in that. Okay, so noise might make you take wrong decisions. All right. Yes, absolutely. So in our control system topology, noise only affects the behavior of the controller, because the controller is receiving the sensor's output, right? Essentially the sensor's output and comparing with the reference. Okay. But in a secondary sense, you would see the noise is also indirectly affecting the control system, because the controller is responsible for generating the manipulated variable, okay, which is controlling the system itself. So it is indirectly affecting the control system. So it is indirectly affecting the control system, not directly affecting. It is directly affecting the sensor, okay, and by affecting the sensor, it is directly affecting, or rather, affecting the controller. And because it is affecting the controller, it is affecting the control system, but it's not directly affecting the control system. No, okay. Yes, we need good quality sensors that are immune to noise, or if they are, what should I say, if noise cannot be avoided, then we need some mechanisms. So sensors, again, the sensor term is essentially, sensors are transducers plus signal conditioning. Transducers plus signal conditioning. Transducers are physical things that actually convert one energy type to another. For example, you want to measure speed, okay, use a tachometer. Tachometer is essentially a motor, or rather a generator, that actually generates voltage based on how fast it is rotating, right? So use a tachometer, so it will actually generate a voltage in the output, and then you need to have some circuitry to make that into a proper reading or something, right? So sensors are essentially transducers in combination with electrical circuits or electronic circuits called signal conditioning circuits. Taken together, they are called sensors. So of course you have to take care of the noise in there. Okay, if there are large amount of noise, you need to take care of that. Okay, to make sure that the noise stays at a minimum level. Okay, because having noise is pretty much undesirable. Okay, it will help you take wrong decisions. It will make you take wrong decisions, which are bad things, right? It will make the controller take wrong decisions. Okay, which is bad. Okay, I talked about tachometer, TACHO, tachometer. Okay, tachometer is used for speed measurement. And of course, nowadays it is not, but back in the day, tachometers were used for speed measurement. Nowadays, we use rotary encoders to actually measure speed, which is very immune to noise by definition. Or someone is saying we are never taught the fabrication process of sensors. Yes, I think you get a paper on measurement, instrumentation, I guess, and there you might study some of that. Not sure entirely. Yes, the fabrication process is a part of material science, not electrical engineering, to be very honest. All right, so that's going to be the end of today's discussion. Feel free to ask any question. I'll be waiting here for just 1 or 2 more minutes. If you have any query, feel free to ask. Otherwise, we're going to end the stream right here. I believe all of you had a good experience here. No issues. Yeah, so the idea is, okay, someone is asking about the tachometer. Okay, you can just do a Google search on tacho generator or tachometer. Essentially, the idea is that if you have a permanent magnet DC motor, for example, permanent magnet DC generator, okay, DC motor, same thing. Okay, if you make the rotor rotate, okay, the voltage generated by the motor will be voltage generated by the generator will be proportional to the speed, ideally. Okay, for an ideal generator, the voltage generated by the generator is proportional to the speed, and based on that we generate a proportional voltage, essentially, right? Right. Subtracting the speeds using a mechanism, how do you subtract speeds? You cannot really. Instead, what you can do, you can actually subtract two voltage values. So you need some mechanism to convert speeds into voltage values, right? For example, so electrical signals, essentially. So we try to convert mechanical signals into electrical signals. So transducers are those things that convert mechanical signals like rotational speed, like pressure, like speed, like humidity, all those mechanical signals into electrical signals, which are useful, more usable rather. And nowadays, okay, for speed measurement for vehicles, if you buy a bike or a car nowadays, it will not have a tachometer at all. Instead, it will have a rotary encoder. Okay, a digital way of measuring speed. Okay, it will have a rotary encoder, a digital way of measuring speed, and it is quite immune to noise by definition. So that's it. Yes. So that's the basic control system topology, and later in the next class we're going to see how we can actually simplify this model. So we will start with simplification in our mind. All right. So I think all clear. Anything else you might want to ask? Otherwise, we're going to end the discussion here. So I would just mention one thing. All of you who are present here, just if you haven't said anything so far, just say something so that I actually use an API and get your names. Okay, for the sake of attendance, of course. Anyway, so thank you very much. I will see you in the next class.